The next thing to look at is numerical integration, and recall that we've learned how to do the trapezoidal rule, the Simpson's rule, and the Simpson's 3/8 rule. So here are some sample scripts that run these different numerical integration approximations. And again, just as I did in the finite difference video a moment ago, let me just copy over the usage. And again, suppose I could just type this as quickly as copy and paste. Okay, and when F, A, B, and N are entered in, N is, remember, the number of panels that we're going to use the trapezoidal integration over. Now, I can, oh, and let's see, I'll have to switch back over to a different folder. Okay, there. And now if I type in trap, and it will prompt me, yes, to type in F, A, B, N. Okay. And now this is a little anticlimactic. What just happened? Well, I just computed the integral from 0 to 1 of e to the cosine x with 20 panels of trapezoidal rule. And it just gives me a single number. I can display that number and take a look at it. Aside from that, nothing very interesting. What I can also do now, though, is likewise, in a very similar way, construct the Simpson's rule approximation. Okay, and notice here, let me copy, in fact, paste this. Okay, all right, and there's S, and there's T, and here, perhaps I want to display both of them. So let me display T on one line, and then a semicolon, S on the next line, and I'll close those brackets, and that'll display as a column vector, T and S, the trapezoidal and the Simpson's rule approximations, which we can see are quite close. Just a coincidence that we have 7, 7 at the end of both, but notice that the 5 is the first place where they have a discrepancy. So this integral is around 2.341. And finally, just to complete everything, and take a look, we can do this with the Simpson's 3/8 rule as well. I don't want to call this S for fear of overwriting the original Simpson's rule. Let's call it perhaps R then. Ah, and that's a good thing, the warning. So this is something that I've written into my program, and it's telling us the results aren't going to be very accurate because I didn't pick the right number of panels. It has to be a multiple of 3. And is the accuracy affected? You bet it is. Let's take a look and see. Ah, 2.34, so much agreement. The presumably fourth order accurate Simpson's 3/8 rule didn't get the right number of decimals. So how can we fix this? Let's try changing n to a multiple of 3 and also a multiple of 2, let's say. So how about 24 instead? That'll fit the bill. Okay. And so let's see. T equals trap, S equals Simpsons, and R is the Simpsons 3/8. And let's display the 3 results. There we go. And the second order accurate rule gives us 2.5 decimals of accuracy. It looks like these fourth order accurate rules at least agree out to 6 decimals, which is pretty reasonable considering the value of h is going to be replicated here, b minus a over n, 0.04. And so h to the 4th is around 6 decimals. That's not a coincidence. Okay. So now the next thing to do is look at a refinement table. So we've got our ability to run our methods. So we'll construct a refinement table now. Okay, and the way these look is we're going to display h, and then the error, and then the rate of convergence of the error, which is something that I'll have to show you what it means. Okay, so the first thing we'll do is set up some values of well, n in this case, in fact, because we were told in the assignment n, h should be 0.5, 0.25, 0.125, and 0.0625, but the interval is going to be from 0 to 1. Okay. So let's say then that n, the values of n, are going to be, well, let's see, h is 0.5, 2, 4, 8, and 16, because 1 over 16 is this 0.0625. In other words, b minus a over n is the value of h. H will be 0.5, 0.25, etc. Okay. Alright, and let's say that k is the length of n, meaning 4 in this case. And let's take little k, ranging from 1 through capital K. Alright, and in this for loop that I'm defining, what I'd like to do is construct an approximation of the integral for each of my rules. So, without really going into the specifics yet, I'd like to do the following. Tk is equal to trap FAB, and then I have to decide how to get the current value of n, that is the kth value of n. So that means that up here I have to say something like the following. Let's say nk. Nk is equal to the kth number from my list of n's. So in this for loop, k goes from 1 through 4. As I come into my for loop, I'll have k equal to 1 initially. If I select n of 1, that's going to pull 2 out of this list. As I go through and k goes from 1 to 2 in my for loop, we'll say now select n of 2. And the second number of n is 4. So this will tell me in sequence to take 2, 4, 8, and then 16 for the values of n. And now I can write nk. So this will construct the trap rule with 2, then 4, then 8, then 16 points, and store those results in capital T1, capital T2, 3, and 4. Okay. Also in my for loop, I'd like to define the Simpson's rule and the Simpson's 3/8 rule. Okay. And then the last thing I'd like to do is define the errors. So let's do error from the trap rule. And again, I'm backfilling some of this, but what I'd like to be able to do is have an exact value for my integral up here. Let's call that I. And, well, I don't know what it is yet. I haven't decided what f of x is yet, but let me put a placeholder in here for just a moment. Okay. But presumably then, the error would be I, let's say the absolute error, is the absolute value of I minus t of k. And in fact, what I'm going to do is just sort of rearrange my for loop so that I have some matching terms here like this. Okay, that syntax applies here for the Simpson's rule and for the Simpson's 3/8 rule. Which I'll call again R. Okay, so now what is this for loop doing? It's looping through values of n from 2, 4, 8, and 16, which will mean that h is 0.5 on downward to 0.0625. Select each value of n, load it up to the trap rule, compute the error. Load it up into the Simpson's rule, compute the error. And load it up into the Simpson's 3/8 rule, and compute the error. Okay. And finally, what we need to look at is the rate of convergence. Okay, so what we'll do now is we'll say that the rate for the trap rule. Okay, and because I didn't show this in class, I'm just going to take a little bit of a shortcut here. Okay, and what this will do is this will fill in for us the final column, the rate of convergence. And what this log2 and everything is doing is selecting for us the parameter, the exponent of whatever power of h there is in the error terms for each rule. Okay, so if the error is around h squared, rate should look like 2. And if the error is 4th order, as we expect it to be for Simpson's rule, this rate should be around 4. These are numerical values. They won't be exact, but they should be close enough that we can see that they're basically integers, usually something like if it's supposed to be second order, we'll see 1.9 or 1.98 or 2.03 or something of that sort. Now, there's one more thing to do then. Let's pick on a value for our integration. If I'm going to integrate from 0 to 1, let's do something that we know the value of for testing, something like a 4x cubed. Okay, so I'm going to integrate 4x cubed, and if I integrate 4x cubed, I'll get x to the 4th over 4, and the 4 cancels. Plug in my upper and lower limits, the exact integral should be 1, so that's a nice convenient choice. Okay, and we've built a lot, and let's run all of this and see what happens. And I can tell you right now, there's one thing that's going to go wrong. Can you predict what it is? Let's see what happened. Whoops, that wasn't what I wanted to focus on. Let me run this section. Now it's going to give me some errors here. This is because I have things in different folders. Oh, I see. It's running fine. Okay. So here, let's display then. Let's see. Let's display the seem to be working because of the other folder. So hold on just one moment. I'll have to reset this a little bit.